Okay, so looking at question 3. Show that the acceleration due to gravity on Mars is 3.71 meters per second. So that's g. We're told that this is a pendulum and it takes 9.24 seconds to undergo 3 oscillations. And we're given the length of the pendulum here. And we're given an amplitude, but that's not really relevant for this first part. Okay, so the acceleration due to gravity on Mars is 3.71. So we're going to use the fact that t is equal to 2 pi root L over g. We need to convert this to t first. T is equal to 9.24 over 3, which is 3.08 seconds. And then we need to rearrange the equation here. So we can say, therefore, we get t squared is equal to 4 pi squared L over g. So therefore, g is equal to 4 pi squared L over t squared, which is equal to 4 pi squared times 0.892 over 3.08 squared, which is equal to 4 times which is 3.71 meters per second squared. Some people argue that measuring more than one pendulum swing is inaccurate as the pendulum winds down. Draw a graph to show that while the pendulum does wind down, this does not affect the accuracy of the method. Use the axes below to show the displacement of the pendulum varies with time over 3 complete oscillations. Assume that the pendulum is released in the position shown, initially with 0 velocity. Label the axes clearly. Okay, so we see that it's released from 12 centimeters, so let's draw that in first. So maybe we'll go 1, 2, 3, 4. 1, 2, 3, 4. So that's 12. This is x in centimeters. And that's negative 12. Maybe we should show also that we know that it's going to decay exponentially. So we'll draw in an exponential decay envelope here. Something like that. And then we want to do 3 full periods. So we'll take this horizontal axis and we'll go maybe 5 centimeters per period, maybe 4 centimeters per period. 4, 8, 12, and we'll divide each of those into 4 so we can draw our sinusoidal curve. And it starts at its maximum position, the position shown. And we can call that either negative or positive maximum, it doesn't matter. So I'll just start at positive maximum. So it's going to go there, 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 and back to there. This is first oscillation, and then the second, and then the third. Okay, and it's important that we show that the period remains constant. We'll label in that as well. That's 3.08, that's 6.16, and this is 9.24, and this is time in seconds. And then we draw in our sine curve as best we can. Something like that. Okay. So there's our fully labeled diagram of it winding down and showing that the period remains constant anyway. So it doesn't matter that it's winding down. Okay, Mark makes a machine to mix Martian dirt with organic matter. He has a small oscillator that moves at 30 hertz. So that's the driving frequency. Mark finds that when the can has a mass of 10.7 kilograms, there's a large oscillation, but when the can has 80% less mass, 80% of the mass, so 20% less, the amplitude of oscillation is less. Overloaded cans also oscillate less. Discuss why the oscillation is large for one specific mass and explain how the spring should be adjusted to get the large oscillation when there's only 80% of the usual mass. Okay, so oscillations will resonate when driving frequency, which is 30 Hertz, matches the natural frequency of the system. Okay. The natural frequency depends on both the mass and the stiffness of the spring. As T is equal to 2 pi square root m over k. If the mass is reduced, the period will change, and therefore the natural frequency will change and no longer match the frequency, the driving frequency. Maybe we should be more specific than saying that change. If the mass is reduced, the period will drop or decrease and no longer match the driving frequency. To achieve resonance with the same driving frequency, we need to, with the same driving frequency but less mass, we need to decrease the spring stiffness, the spring constant, we can say, by the same amount. I.e., use a spring stiffness of 0.8 K. So that the natural frequency once again is 30 Hertz. Okay, and the final part of this question. The can is oscillating with an amplitude of 12.2 millimeters, so that's A. To stop the can in the correct position, Mark must make this machine turn off when it has 3.21 millimeters left to travel to the center position. So in other words, it starts here. Timer starts at t equals 0 when the can is at its maximum displacement. So it starts here, it's heading up towards center. When it's 3.21 millimeters away, it has to be turned off, and then it'll travel on to the center position. So this distance here is 3.21. This distance here is the amplitude, which is 12.2. Okay, so looking at the reference circle, our phasor is going to start here at the maximum displacement, which is here. You could start at positive maximum, you'd get the same answer, but we'll start at lower maximum, and it's going to be turned off when it's here. So we can draw that phasor in there as well. Okay, and then we can label in the angle here, theta. And then we can label in the distances that we know. So I'm going to draw in a dotted line here. And we know that the phasor's length is 12.2. And we know that this short side here, this is where we need to turn it off. That's 3.21. And now we can use the phasor to figure out the angle, and then figure out what proportion of a full circle that is, and multiply that fraction by the time period, which we have from the previous question. So, to find theta, we know that adjacent over hypotenuse, 3.21 over 12.2 is equal to cosine of theta. So, theta is equal to inverse cosine of 3.21 over 12.2. So we can say shift cos 3.21 divided by 12.2, which gives us 74.745 degrees. Then we need to get t as well. In our last part of the question, we had t, f is 30 hertz. We know t is equal to 1 over f, which is equal to 1 divided by 30 is 0.033 seconds. And then we know that the time that's elapsed, which is what we're trying to find, the time that's elapsed from the maximum position to when it gets to 3.21 when we want to turn it off, divided by t, must be equal to 74.745 over 360. So the proportion of the full circle that that phasor is spun through. So little t is going to be equal to 0.033 times 74.745 over 360, which is 74.745 divided by 360 is 6.92 times 10 to the minus 3 seconds. That's one method. The other method we can use is using the equation. So in this case, the oscillator starts at maximum, so we're going to use the displacement. X is equal to A cos omega t. Omega is 2 pi f, which is 2 pi times 30, 2 times pi times 30, which is 188.5, we can say, radians per second. And we know we want to use radians here. We want to rearrange this for t first. So we go x over a is equal to cos omega t. So omega t is equal to the inverse cosine of x over a. So t is equal to 1 over omega inverse cosine x over a, which is equal to 1 over 188.5 times the inverse cosine of 3.21 over 12.2. And we need to be in radians for this, so we need to just shift our calculator to radians, and then we just plug in the numbers. Which is 6.92, not surprisingly, times 10 to the minus 3 seconds, which is exactly the same as the other answer. So either method would give you excellence for that question. Cool, so that's it. Any questions, let me know.